Welcome everyone. Grab a seat. I am absolutely thrilled to have you all here in today's explainer because, well, we're going to be deconstructing what is arguably the most ambitious engineering roadmap in all of human history. We're talking about the literal pathway to an interplanetary future. And look, we're not just geeking out over abstract science fiction today. No, we are diving into a very real, multi-trillion-dollar logistical megaproject that was announced back in March 2026. It's called the Terafab case study, and it is basically our blueprint for humanity's massive leap toward becoming a Type 2 civilization. Let's get into it. So here's our syllabus for today's explainer. We'll start with the Type 2 blueprint, move on to Earth's mega infrastructure, that's the Terafab project, then look at Martian robotic automation, the artificial magnetosphere, and finally, we'll wrap up with a rigorous engineering risk assessment.
All right, Section 1, the Type 2 blueprint, theoretical framework.
Now, to really wrap our heads around the factories being built right now, today, you kind of have to understand the sheer astronomical scale of what they're designed to achieve tomorrow. Let's look at this foundational concept. A Type 2 civilization is basically a society that has unlocked the ultimate God mode when it comes to energy production. We're talking about having total, absolute control over their host star's output. And the blueprint to pull this off relies heavily on a theoretical megastructure called a Dyson swarm. So instead of building a solid shell around the sun, imagine millions, or honestly billions, of smart satellites deployed 150 million kilometers away, creating this vast, incredibly complex web. These satellites would capture the sun's unfiltered, colossal energy output, energy that right now just radiates uselessly into the void of space, and beam it wirelessly, using microwaves or high-intensity lasers, directly back to Earth, and more importantly for us, to Mars.
And that brings us to this metric, which brilliantly illustrates exactly why a Dyson swarm is a literal prerequisite for colonizing Mars. Look at that number. Mars only gets about 43% of the solar intensity that we enjoy here on Earth. So if we try to rely on our standard Earthbound solar power models on the Martian surface, they fail miserably. You simply cannot build massive, high-tech cities relying on weak, filtered sunlight. You absolutely need a space-based solar network up there, beaming down an infinite continuous power grid.
Okay, let's bring it back home. Section 2, Earth's mega infrastructure, Terafab.
Moving from astrophysics theory to what's actually being built right now, let's look at the terrestrial infrastructure that makes this all possible. We're talking about a massive joint venture between Tesla, SpaceX, and Intel. Just look at the sheer economic and industrial scale here. It's unprecedented. This is a vertically integrated semiconductor fabrication plant. The prototype phase alone, located near Giga Texas in Austin, is a $119 billion investment, just for the prototype. And it's designed so they can iterate rapidly without ever needing to ship wafers between different sites. But when you look at the full-scale facility planned for Grimes County, the numbers become truly astronomical. Analysts are projecting an investment anywhere between $5 to $13 trillion to build a manufacturing complex spanning 10 million square meters. If they pull this off, it'll easily be one of the largest factories ever constructed on the face of the Earth.
And that massive facility has a very specific, jaw-dropping production target: 100 to 200 billion custom AI and memory chips per year. The global chip industry as it stands today simply cannot expand fast enough to meet the demand required for an interplanetary push. Terafab is stepping in to utilize incredibly advanced 2nm and Intel 14A manufacturing processes. And they aren't making standard consumer electronics chips. No, these are specifically designed for edge inference compute. Basically, they're optimized to run orbital AI infrastructure, millions of Tesla vehicles, and the vast armies of autonomous humanoid robots we'll need for off-world construction.
But that raises a pretty big question, right? How on earth do you get billions of micro-scale AI chips and massive, heavy factory equipment all the way into space? Well, you need a macro-scale delivery system. Enter Starship version 3. This is the crucial interplanetary delivery truck that makes this entire architectural blueprint remotely possible. Standing over 124 meters tall, it is literally the largest rocket in human history. It's equipped with new generation Raptor 3 engines that punch out 50% more thrust than their predecessors, giving it a staggering 100 to 100-ton payload capacity. The idea is that it can haul entire Terafab factory components and miles of those solar sheets into orbit in a single flight.
This takes us perfectly to Section 3, Martian robotic automation. So, what actually happens when those massive 200-ton payloads of heavy machinery and AI chips finally touch down on the Martian surface? Well, before human astronauts even arrive, which is targeted for around the year 2030, by the way, there's a highly precise, fully autonomous construction procedure that has to happen. Step 1, Starship lands its payload of heavy machinery. Step 2, an army of Tesla Optimus robots, running on those exact AI chips manufactured back at Terafab, gets to work harvesting the local Martian dust, or to use the scientific term, regolith. Step 3, massive 3D printers, powered by that orbital solar energy we talked about, process that raw regolith into concrete-strength walls, metal structures, and life-saving radiation domes.
This quote from the literature really hit the nail on the head, bringing the reality of Martian logistics to life. Imagine the Martian wasteland where thousands of robots work tirelessly, day and night, without oxygen, laying roads and raising radiation domes. I mean, think about it. We can't just ship thousands of tons of cement and steel from Earth. It costs millions of dollars to send a single kilogram to Mars. So the entire supply chain has to be local, and it has to be completely autonomous. These robotic fleets are going to operate entirely without human intervention. No sleep, no life support systems required. Their one and only job is to build a high-tech, ready-to-live colony so that when the first astronauts finally step onto the red planet, their city is already built and waiting for them.
All right, moving on to Section 4, the artificial magnetosphere.
Let's shift our focus back to planetary-scale engineering for a moment, because we have to talk about the most severe, invisible hurdle to settling Mars: cosmic radiation. Notice the stark contrast here between Earth's natural defenses and the proposed engineering solution for Mars. Billions of years ago, Mars actually lost its natural magnetic shield, which allowed brutal solar winds to constantly strip away its atmosphere. To fix this, engineers are proposing something absolutely wild: deploying an artificial superconducting magnetic dipole at a specific gravitational balance point between the Sun and Mars, which is known as the L1 Lagrange point.
Now, I know that sounds like pure sci-fi, but it is a strictly calculated physics proposal. This colossal electromagnet would be continuously powered by the energy harvested from our Dyson swarm. Sitting right there between the Sun and Mars, it would act as this invisible, massive shield, deflecting lethal solar winds and cancer-causing particles before they even have a chance to reach the planet. And here's where it gets really interesting. Once Mars is shielded, the frozen CO2 locked inside the planet would begin to trap heat, kicking off a natural greenhouse effect. So this single engineering megaproject is actually the crucial first step in large-scale planetary terraforming, theoretically making the red planet breathable over the course of a few centuries.
Which brings us to our final topic today, Section 5, Engineering Risk Assessment.
To wrap up our analysis, we have to ground ourselves in reality and conduct a rigorous evaluation of the operational risks. Because doing this on the scale, the stakes are incredibly high. We need to acknowledge the severe points of failure in the Terafab vision. We are talking about operating highly sensitive manufacturing hardware in completely hostile, unforgiving environments. First off, zero gravity can cause completely unexpected degradation of delicate fabrication components. Second, and honestly perhaps the most critical bottleneck, is that the intense cosmic radiation in deep space could just permanently destroy those microscopic 2-nanometer AI circuits before we even have a chance to shield them. And finally, we have to account for these autonomous robotic fleets suddenly malfunctioning during Mars's infamous planet-wide dust storms. The bottom line is this: if these sensitive hardware components succumb to zero-G or radiation, this entire multi-trillion-dollar space-based economy could just instantly collapse.
Which leaves us with this final, quite provocative question to ponder as we end today's lecture. Looking at the data we've covered, the literally trillions of dollars invested in the Terafab AI facilities, the staggering power of the Starship V3, and the monumental, terrifying challenges of radiation and orbital mechanics, what do you conclude? Is humanity's leap to a Type 2 civilization an inevitable engineering triumph that we are actually going to witness in our lifetimes? Or is it just a logistical impossibility that's destined to remain a drawing board pipe dream? I really encourage you to critically assess the feasibility of everything we've covered today. Thank you so much for joining this explainer, and as always, keep questioning the limits of what's actually possible. See you next time.